Today we're going to be talking about proportions and the golden rectangle. So let's go through a little bit of vocabulary before we begin the actual unit here. The first vocabulary that we need to know is ratio. What is a ratio? A ratio, whoa, let's see if I can reduce that thickness here. Alright, much better. Is a comparison of quantities. Comparison of quantities. Alright, and we'll use ratios in things like scale. If I have a ground plan that says that every inch on the paper is a foot on my construction site, then that's a ratio. That's a comparison of quantities. And proportion is a statement that two ratios are equal. So we might say as a proportion, we might say the ratio A to B is equal to C to D. Now an example of this might be 1/2 is equal to 4/8. They're both the same value. It's just that one we've got that looks a little bit larger than the numerators, or this one looks, the numerators on here look larger than this one, but the numerator is enlarged by the same amount as the denominator. The 1 was multiplied by 4 to get 4, and then the 2 was multiplied by 4 to get 8. So this ratio was multiplied by the same number with numerator and denominator to get that ratio. Alright, let's take a look at example 1. Example 1 said the ratio of side lengths of a quadrilateral is 2, 3, 5, and 7, and its perimeter is 85 feet. What is the length of each side? So when we're doing ratios like this, the easiest way to address something like that is just to put an x after each number. 2x, 3x, 5x, and 7x. And so our quadrilateral might look, of course this is not drawn to scale, but our quadrilateral might look something like this. 2x, 3x, 5x, and 7x. And then we know that the perimeter of this whole thing is 85, right? So we just say 85 equals 2x plus 3x plus 5x plus 7x, and that turns into 85 equals 17x. And then of course you divide both sides by by 17. And now we get x equals 5. Alright, so the big thing I want you to remember from this is that if you see a ratio lined up like this, I just want you to put an x after each of those numbers, and then you can solve from there. Example 2 wants you to solve this equation here. Now we're going back to algebra in this one. We're cross multiplying, and so for my 8 moves up to my 5, and I get 8 times 5. Well, 8 times 5 is 40. And then my other side is a little bit more difficult. X minus 3 times 2x minus 4. You gotta scoot this over here. 2x minus 4, x minus 3. Alright, and if you remember how to solve these, we just multiply the front first, and then we can multiply the outer times each other, and then the inner times each other, and then the last two. So the first multiplied times each other, 2x squared. And then the outer multiplied times each other, we got our negative 4x. The inner multiplied times each other are negative 6x. And then the last is positive 12. And then of course I'm going to combine my like terms here. So negative 4x and negative 6x gives me negative 10x. 2x squared minus 10x plus 12. As you can see, this takes up a lot of room. Is equal to 40. And so I'm going to subtract 40 from both sides because I want to try to get this side of the equation here at 0, and that's how I'm solving my quadratic formula. So I come up with 2x squared minus 10x, and then positive 12 minus 40 is minus 28. And that's all equal to 0, right? Okay. Well, here's where that quadratic equation, the quadratic formula, rears its ugly head. So we've got, this is our A, this is our B, and this is our C. And I don't know if you remember this from algebra, but our quadratic formula says that x equals negative b, here we'll zoom out a little bit, negative b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to plug in our A, which is 2, our B, which is negative 10, and our C, which is negative 28, to our A, B's, and C's over here, and we'll get our answers. So we've got x equals, and negative B is 10 plus or minus the square root of, come out a little bit more, plus or minus the square root of b squared, which is 100, minus 4 times a, which is 2, so 4 times 2 is 8, and 8 times 28, or negative 28. So that is negative 224. So change that to positive 224. And you divide all that by 2a. So a is 2, 2a is 4. So that boils down to x equals 10 plus or minus the square root of 324 all over 4. The square root of 324 is 18, so 10 plus or minus 18 over 4. So that goes to, right out of space here. If it's 10 plus 18 over 4, that's 28 over 4. And if it's 10 minus 18 over 4, that's negative 8 over 4. And of course, 28 over 4 is 7, and negative 8 over 4 is negative 2. So after all of that, we've got our answers right here. X is equal to 7 and negative 2. Goodness gracious, look at all that math. Alright, well, let's erase a whole bunch of this here. There you go. Oh, I hate to see you go. And we'll look at example number 3. Okay, given that 18c is equal to 24d, we've got to find the ratio of dc here. That's d to c in the simplest form. Well, when you see d to c like that, here's what I want you to think of. I want you to take this c and put it under here. Take this little guy and turn it around, and we will just make that a ratio. So d over c. So d to c just means d over c, right? Now we've got to get this guy into this formation. 18c equals 24d into this formation right here. So we'll start with 18c equals 24d, right? Once again, I want the d to be on top and the c to be on bottom, so I'm just going to divide both sides by c, right? Now I've got my d on top and my c on bottom. Of course, my c's cancel out, and I'm just left with 18 equals 24d over c. So now I just need to get this 24 to the other side. And how do I do that? I multiply both sides by 1 over 24. 1 over 24. And so I end up with 18 over 24 equals d over c. Alright. So let's look at the next example. The next example talks about the golden rectangle. Let me go ahead and erase some of this stuff, because we're going to need the room. Alright, so a golden rectangle it represents the golden ratio. And the golden ratio is this, well, it's a ratio just like the ones we were working with. And It's used in art, it's used in science, and it's this sort of perfect ratio. So before I say anything more about it, let's look at how to construct this ratio, and then I think it'll be more clear as to what it actually is. So we're going to use the square to provide it with side lengths of 2 inches, and then we're going to find the midpoint of side AB by construction and label it M. So if we're finding the midpoint here, we're going to take these 2 points, and remember we're going to take our compass and swing 2 arcs right here, and then that point in the middle is going to be our midpoint. And then we're going to label it M. Then connect the point M and C and find the length of MC using the Pythagorean theorem. So our M and C are going to be this, that line right there. And to find it using the Pythagorean theorem, we know that if M is our midpoint, then AM is going to equal 1 inch, right? And so our hypotenuse is going to be C, so C squared equals A squared plus B squared. There we go. And then C squared equals, let's call our A squared 2 squared. 2 squared is 4, plus B squared is 1 squared, so that's just 1. So C squared equals 5. But remember, we're not looking for C squared, we're looking for C, so we have to take the square root of C squared and the square root of 5, and we end up with C equals the square root of 5, right? So C equals the square root of 5. Now, extend AB past B with compass point M opened to length MC. Alright, so this is basically what this means. Hold on, let me erase all this stuff here. So we are going to be extending AB past B. Okay, but we're only going to go to this compass length here. Okay, so what we're going to do is actually, see, we've got our MC right here. We're going to swing our compass like so. Now, this is not the best, this is not a scientific measurement here. This is kind of just a rough sort of representation. So your compass is going to be a lot more precise. Alright, so we swung that down, that measurement of MC, down over to our line extended past B, and it asks us to label the point E. And it also says with the compass pointed at M, open to length MC, make an arc MC on the extended line. So let's just make that arc right there. It's called E. And next, since AM equals 1, now once again, where this is AM right here, equals 1, and ME right here equals, what does it equal? The square root of 5, remember? So let's write that down. Then the length of AE, the total length from A to E, must be 1, here, AE equals 1 plus the square root of 5, right? Alright, so you'd make a swing through here, a swing through here, and you'd put your compass on that point, and on this point, and from this point, you're going to swing that compass around that way. From this point, you're going to swing that compass around that way, and then so you're left with this line that ideally would go through this point right here. But like I said, this is just a drawing, so it's going to be very imprecise here. Well, this is our F. We're going to extend our line, our CD line, over to F there. Right, so now let me clear out some space. Now that we've got all of that constructed and all of that craziness done with here, I'm going to take away this part. Boom. Okay. Okay. Now we have our rectangle CFEA. CFEA. And number 8 is compare the ratio of AE, which is this whole line right here, to AC, which is this side. So this side of our new rectangle to this side, which was formerly the side of our square, right? We're going to compare that ratio to the ratio for FE and EB by converting each ratio to a decimal. Okay, we're going to back up a little bit here so we can get a better view. Well, let's take a look at AE. AE, this whole thing, we said that it was, well, first of all, we're going to say that we're going to make sure we know how our ratio looks, AE over AC. So that just equals AE is 1 plus the square root of 5 over AC, and remember AC is just this side of our square over 2. And then we're going to enter that into the calculator, and you should get something approximately 1.618. Alright? Now we're going to do FE and EB. And remember that FE is this side right here, and EB is this side right here. So FE is going to be 2 because that's still the side of the square, and then BE we decided right over here would be the square root of 5 minus 1. So FE over EB, that is 2 divided by EB, square root of 5 minus 1. We're going to plug that into our calculator, and we're going to get 1.618. Now that's the same ratio, as you can see, as AE over AC. Alright, so what does this all mean? This means that AE is 1.618 times the length of AC, and FE is 1.618 times the length of EB. Let's look at that. Let me draw this rectangle again, and we can kind of take a look at what that means. And we had A, C, and right about there, I think, D, F, E, B, right? And we said that AE is 1.618 times AC. So if AC were 1, AE would be 1.618. 1.618. And FE is 1.618 times EB. So if EB were 1, then FE would be 1.618. Alright, so that's a little bit confusing. What's the significance of this? So let's do it, let's take a look at it this way. If I were to take this part off now that I have my new rectangle, and I were to switch it here, now this rectangle would be exactly the same proportion as my old rectangle that this came off of. 1 and 1 point, here, I'll move this up a little bit, 1 and 1.618, right? Here, let me draw the other side of this rectangle. Now, what do you think would happen if I cut this off and this side here? This side was one of my square. This side was one of my square. And now remember, my new ratio is, well, here. This shouldn't be so far out that way. That would be more like that. My new ratio for this is 1.618 to 1 just on this side right here, right? And if I took this part, of my rectangle off and left it with just the square and turned it around again just like that, then I would have another of the exact same shape where I would have my square 1 to 1, and this whole side, of course, would be 1.618. Let's say this is 1.618 is this whole side right here. And then I'm not doing a very good job with the there we go, the golden rectangle. And then of course now the ratio of this side to this side is 1.618 to 1. And I could keep on going like this forever. So you see that no matter how many times I cut off this rectangle, this new smaller rectangle I've made by cutting off this square part, it's always going to be a ratio of 1.618 to 1. 1.618 to 1. 1.618 to 1. And that's the golden rectangle. So part 2 here, what distinguishes the golden rectangle from other rectangles is the ratio of length to width. Now it says the rectangle shown is a golden rectangle. Its length is 1 and its width is x. A square with a side length equal to the width of the rectangle is drawn inside the rectangle, as you can see. The remainder of the original rectangle is a rectangle that is similar to the original, so that the ratios of corresponding sides are proportional. Okay. Let's take a look at what this really means. Here you have a square drawn inside our golden rectangle, right? Alright, so once you've cut that square out of the golden rectangle, you're left with this rectangle here. Make sense? Now watch what happens when we take that rectangle, we move it, and we explode it here. We get the same rectangle as the bigger one. It's got exactly the same proportions. So, what if we erase this and we drew this rectangle again, and this time we said, alright, well, last time when we took out a square, the remaining rectangle was proportional to my large rectangle. So what if I kind of do the same thing this time? What if I take my square, try to place it as strategically as I can right there. Okay, that looks good. And now, where's my remaining rectangle of the yellow rectangle? Right here, right? So what do you think is going to happen with this purple rectangle? If I enlarge this purple rectangle, zoop, guess what? It's exactly proportional with the larger rectangle. And that will go on and on and on. And that's really why this is called the golden rectangle, because I can take this square, I can move it down to the next thing. Now this is going to be an unscientific rectangle here, I can tell you that right now. But it'll be kind of proportional, and that rectangle will be proportional. So it just keeps on moving down and down and down and down and down. And that's why this golden rectangle really is, well, that's why they call it the golden rectangle, because it's the only proportion of these two sides that makes it so you can keep on drilling down and drilling down and drilling down and drilling down and drilling down, and you'll still have, after you take out that square, you'll still have a rectangle of the same exact proportion as the rectangle that you started with. That is 1 to 1.618, no matter how small you get. That's going to be your proportion right there. Pretty cool stuff, huh? Okay, so now let's see what it's asking us to do with question 1. Use the segment addition postulate, part plus part equals whole, to write an equation relating x and y. Alright, well now that I've messed all this stuff up, let me erase that and start over. Okay, so we're looking at part plus part equals whole for x and y, and here's my x, and here's my y, and here's my whole deal, right? So x is one part, plus y is another part, equals my whole. 1. Alright, not too shabby. And now we're asked to solve for y. Well, I just subtract x from both sides. These two x's cancel out, and I get y equals 1 minus x, right? Okay. And number 3 says, since the larger rectangle is similar to the smaller rectangle, now remember what that means, that this larger rectangle right here, I can just take and I can turn that into my smaller rectangle that, well, just about like that. That's what it means by similar, right? Since the larger rectangle is similar to the smaller rectangle, then we know that 1 over x, and that's, whoops, hold on. That's our 1 over our x, or this side over that side, right, is equal to our x over y. And remember that this side is x, this side is y, so is equal to our x over y. And one more time, just because it's so fun, this is all that this means. Okay. Doop doop. Trying to get that just perfect there. Okay. I hope I haven't confused you completely. Okay, substitute for y in the proportion so that it is in terms of x only. Well, they're asking you to go back up here and take a look at y equals x, or 1 minus x, and then put that in for this right here. So we'll have 1 over x equals x over, remember this guy right here, 1 minus x. And then cross multiply, alright? So we know that we're going to multiply the quantity 1 minus x times 1, and we're going to multiply x times x. So we get x squared equals 1 minus x, right? Alright, let's move it up. Put all the terms in the equation on the left side of the equals sign to get an equation in the form of ax squared plus bx plus c. So we know that we just need to, let's see, we'll do yellow here. Subtract 1 and add x to both sides. Subtract 1 and add x. And of course 1 minus a negative 1 cancels out, and negative x plus x. So that all equals 0. We have x squared plus x minus 1. See where we got that from, this stuff right here? And that's in our ax squared plus bx plus c format. And now we're going to use the quadratic formula, this guy right here, to find the solutions to the equation and leave the answer as a fraction with a square root in the numerator. So we're going to see what the value of a is right here. Remember, the value of a is just whatever number is in front of x squared, and in this instance it happens to be that a just equals 1, because it's just like 1x squared, right? And then b, in this instance, also equals 1, because that's just the number that's in front of the x, right? And then the c is negative 1 right here, so we're going to just say c equals negative 1. And then we're going to plug all this stuff in to our quadratic formula. So let's see. we've got negative b, which is 1, plus or minus the square root of b squared, well, 1 squared, minus 4ac. 4 times a is 1, so 4 times 1 is 4, times a negative 1 is negative 4. And so this negative is going to turn into a positive 4 all over 2a, and of course a is just 1, so all over 2. And so that just turns into negative 1, we'll say, turns into negative 1 plus or minus the square root of 5 all over 2. And number 8 says, of the two solutions, one is negative and one is positive. And remember, that's just because we have a negative and a positive right here, right? And since x represents a length, we are only interested in the positive value of x. The golden ratio is the reciprocal of this number. Use a calculator to approximate the reciprocal. Give your answer with 3 digits after the decimal. Well, remember that a reciprocal just means 1 over whatever you had, whatever your answer was. And so in this case, a reciprocal of the golden ratio would be 1 over 1.618. So first, let's calculate all of this stuff right here. We can just plug that into the calculator, and so we get that negative 1 plus or minus, well, with this one, remember, it's just going to be plus, because it's a distance, and we're not interested in minus. We're not interested in negative numbers, I mean. Negative 1 plus the square root of 5 all over 2 equals, well, is approximately equal to 0.618. And remember, the reciprocal of a number is just 1 over that, so 1 divided by 0.618 is the reciprocal that we're going to get, and that number is 1.618. And that 1.618, you will definitely want to memorize that number. That's our golden ratio, 1 to 1.618. Okay. Example 4 below is a golden rectangle. Find the dimensions of rectangle A, B, C, D. So we know that the dimension of BC here is 4, right? And we know that AB is X. And so we're going to set that up as a ratio, 4 over X equals, and then we're going to go to our golden rectangle here. We know that a golden rectangle, the long part of the rectangle is 1.618, and then the short part of the rectangle is 1, right? So we're going to set the ratio of the rectangle that we're working with as 4 over 6, and we're going to set that equal to our golden ratio, because we know it's a golden rectangle. Obviously, you could not do this for any rectangle. It has to be established that it is a golden rectangle, right? Alright, so whenever you have an x in the denominator and something else in the numerator, for on the other side of the equation, we can just take that x, we can bring it over to one side, we take that whatever's in the numerator, we bring it over, and we swap them. That's a quick, cheap, and easy way to do that, right? And then so we can just divide in our calculators. We can divide 4 divided by 1.6, and we get x is approximately 2.472. So we know that this side right here is approximately 2.472 if this side is 4. That's our golden ratio. Example number 5, a golden rectangle has a side measuring 7 centimeters. First of all, let's set up our nice golden rectangle there. Find all possible lengths of an adjacent side to the nearest millimeter. Oh man, they don't tell us which side. Alright, well, first we'll assume that the smaller side is 7, okay? And we'll assume, or we'll just say that we do not know what the larger side is, right? Okay, then we can set up another rectangle, and we're going to say that, whoops, boom, boom, we're going to say that the larger side is 7, and the smaller side is x, because once again they don't tell us what side it is. Alright, so in this guy right here, let's put that little triangle right there. That little line right there for the rectangle. It'll be somewhere around there. In this side, we're going to put the larger side, side on top. We have x over 7 equals 1.618 over 1. Always remember, let's just always put that larger side on top when we're establishing the ratio. Okay? And then we just bring our 7 over to this side. We're multiplying it. Boom, 1.618 times 7. And we get that x is approximately 11.326 centimeters, right? But they're trying to be tricky, and they're telling us to find it to the nearest millimeter. So we're going to say that x is approximately 113 millimeters, 113 millimeters. Remember, to find the millimeters from centimeters, you just move the decimal one place to the right. Alright, so basically the same thing here. We're going to set up our ratio first. So remember, I want you to take the whoa, goodness. I want you to take the large side right here, and I want you to put it over the smaller side, alright, as your ratio, okay? And then we'll just take equals the large side of the golden rectangle, and put it over the smaller side. Alright, and once again, whenever we have something like this with the x in the denominator, we can just switch the x, we can just switch the x and whatever is in the numerator on the other side of the equation. And so we get x equals 7 divided by 1.618. And that's going to be, x is approximately 4.326 centimeters. Or in millimeters, x is approximately, remember we just move the decimal one place to the right, And since the next number is 2, we just round down and we get approximately 43 millimeters. All right. So there you have it, the golden rectangle. It is kind of wild, kind of crazy, a little bit tough to understand, but it's a pretty cool thing. If you're into photography, you actually use the golden rectangle a lot. You'll see it in Michelangelo's paintings. You'll see it in the shell of a nautilus. Some people even say that a beautiful face will have the golden ratio in it. But I'll leave that for you to decide. All right, hasta la vista.